You feel it every single second of every day, right? That constant pull towards the Earth. But what if the way we think about gravity is, well, just plain wrong? We're about to dig into a really fascinating paper that suggests gravity isn't a fundamental force at all. Let's get into it. Okay, so let's just get right to the heart of the matter with this one big question. Is gravity a fundamental force? For centuries, we've pretty much taken for granted that it's one of the four basic pillars of reality. But this new model, it suggests it might be something completely different. To really get our heads around this, let's compare two ideas. You've got a fundamental force, which is like a basic ingredient in the universe's cosmic recipe. Think of it like flour. Then you have an emergent phenomenon. Now, this isn't an ingredient itself, but a property that just sort of happens when you combine ingredients. For instance, a single H2O molecule isn't wet, right? But get a whole bunch of them together, and suddenly the property of wetness emerges. This paper is basically arguing that gravity is a lot more like wetness than it is like flour. So why even start questioning gravity's status in the first place? Well, because when you look at the four fundamental forces, gravity has always been the weird one, the odd one out. It is incredibly, incredibly weak compared to the others, and it's been notoriously difficult to unite with quantum mechanics. It just doesn't seem to play by the same rules. And that leads us to the central idea of the paper, which you can see right here. The author is proposing that gravity isn't this standalone thing at all. Instead, it's a large-scale effect that comes from the combined energy of all the other known forces and fields. You see, it's not a primary actor in the play, it's more like a consequence of everyone else's actions on stage. Now, this might sound pretty radical, I get it, but the idea actually has its roots in the work of the master himself, Albert Einstein. This new theory isn't about throwing out general relativity, not at all. It's actually building directly on one of its most profound insights. Let's take a look at something called the stress-energy tensor from Einstein's field equations. You know, we always hear that mass bends space-time, and that's how we get gravity. And that's true, but it's not the whole story. What Einstein actually said was that energy and momentum bend space-time. Mass is just a really, really dense form of energy. The stress-energy tensor is the part of the equation that accounts for all the energy in a system. So here's where this paper makes its really clever logical leap. Step 1. We know from Einstein that the total energy of a system is what causes gravity. So step 2. This paper asks a simple question. What if we stop using a general placeholder for total energy and instead we plug in all of its known individual sources? What happens if we treat every source of energy as an equal contributor to gravity? So if gravity is really the result of the total energy density packed into a region of space, what kinds of energy are we actually talking about? Well, the answer takes us on a little trip deep into the world of quantum field theory. Think of this chart like a recipe for gravity, with a whole bunch of different ingredients. Of course, you've got the energy from mass, good old E equals mc squared, but this model says we also have to include the energy from the electromagnetic field, the strong nuclear force that holds atomic nuclei together, and even the weak nuclear force that's in charge of radioactive decay. And look, this isn't just some abstract theoretical stuff. This is real, measurable energy we're talking about. It's the energy that's buzzing around in electric and magnetic fields, the energy in the gluon fields that act like cosmic superglue for protons and neutrons, and even the energy released by particles like W and Z bosons during subatomic reactions. The argument is that all of this stuff is pitching in to create the gravitational field. Okay, so we have all our ingredients. How do we actually combine them? If gravity is just the sum of all these different energies, how do we write that down as a new recipe? The core concept is actually beautifully simple. It just proposes that the gravitational pull at any single point in space is literally the sum of all the different energy densities in the area around it. It's a direct one-to-one relationship. You just add it all up. And here it is, the proposed formula at the very heart of the paper. Now, I know it looks a little intimidating, but don't worry about the math symbols. The important part is just seeing what it represents. You can literally see the terms from mass energy, electromagnetic energy, the strong force, and the weak force all just being added together inside those brackets. So what does that little g of x actually represent? Well, it's just the local gravitational potential. Basically, the strength of gravity at one specific point, x. The formula defines it as the grand total of all the energy densities from all those different fields in the space right around it. In this picture, gravity isn't some separate force, it's just the final tally of everything else. It's a really elegant and, frankly, provocative idea, right? But what are the real-world implications? Why does reframing gravity this way actually matter for the future of physics? Well, this idea has some absolutely profound implications. First, it means you could have gravity without any mass. Think about it. A region of space filled with nothing but intense light could have its own gravity. Second, by putting all energy sources on a level playing field, it offers a potential bridge between general relativity and quantum mechanics. That's the holy grail of modern physics. And maybe most importantly, this is a testable idea. The theory predicts that gravity should be measurably stronger near things like powerful magnets or particle accelerators, where field energy is off the charts. So this isn't just philosophy, it's a direct call to go out and run some new experiments. And this leaves us with a final, truly mind-bending question to chew on. Is gravity one of the fundamental pillars holding up the universe? Or is it something even more profound? Just the visible, macroscopic shape of all the combined energy flowing through space-time? This paper suggests it's the latter, and if it's right, well, that could change everything we think we know.